Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this video is part 2 of our larger video on the one-way analysis of variance, or the one-way ANOVA. Now, in part 1, we went over an example problem and really sort of took it apart and looked at how all the parts of the one-way ANOVA fit together. So in part 2, we're going to go into Microsoft Excel and do a, quote, hand calculation of the one-way ANOVA. So if you're watching the video on YouTube, you can go to the description below the video, and there you'll find a link to the corresponding blog post for this problem. On the blog post, you can actually download a blank version of the Excel file we're going to use, and you can follow along step by step. So without further waiting, let's go ahead and get started on part 2 of the one-way analysis of variance. Now, what we're going to do in Excel is try to replicate the output in SPSS. And again, SPSS is the statistical software I use in my work. So I went ahead and did our example problem in SPSS, and this was the result. So we're going to go into Excel and actually try to replicate this ANOVA chart doing hand calculations. And of course, I don't mean literally by hand. We're going to use Excel formulas. But in the end, we want to have a chart that looks exactly like this. Now, before we actually go into Excel, we do have to go over a few formulas for the one-way ANOVA. Now, I mentioned before that some textbooks and some professors and classes and everything else call the same things by different names. So you may have to cross-reference what we're going to learn here with how it's presented in your class. So you may actually want to have your textbook open or your notes open as we go through it. It's the same thing, but again, they go by different names depending on what text you're using or what professor you have. So before we do that, I just want to point out what's going to come up here in a second. When you see the variable n, or the large N, that represents the total number of observations in our experiment, or in our problem. In this case, it's 21, remember. Now, C is the number of columns we have in our chart. And remember, in this problem, we had 3, because we had 3 years of students. So let's talk about SSC. Remember, that's sum of squares of the columns, or sometimes what's called the treatments. It's also the levels of our single factor we're looking at. Remember, I said they can go by different names. That's what I mean. So in this case, we had year 1, year 2, and year 3. Those are our columns. Now, the SSC also has a degrees of freedom. Actually, all these have their own degrees of freedom. In the SSC case, the degrees of freedom of the columns is C minus 1. Now, the MSC is the mean squared of the columns. So mean square of the columns. That's MSC. and that is the SSC, so the sum of squares of the columns, divided by its own degrees of freedom. And again, this is all very abstract until we do it, so just hang with me. So the SSE is the sum of the squares of the error, or the within each column, each individual column, sum of squares. So the SSC is the sum of squares between the columns. The SSE is the sum of squares within each column. So the degrees of freedom for SSC is n minus c. And again, we'll put numbers on all these here in a minute. So the MSE is the mean squared error. Now the MSE is very important in many areas of statistics, so keep that in the back of your head as we proceed. But MSE is the mean squared of the error. And that is the SSE divided by the degrees of freedom for the error. And then we have SST, which of course is the sum of squares of the total sum of squares. The degrees of freedom for the SST is n minus 1. So the total number of observations minus 1. Now in the end, we will end up with an F statistic. Remember way back when on our F-stat video what the F statistic is? It's a ratio. The F ratio is a ratio of two variances. So in our F ratio here, in the numerator, we're going to have the mean sum of squares for the columns, which is the variance between the columns. And then in the denominator, we're going to have the mean squared error, which is the variance of the sum of squares inside the columns. So we have between the columns on top and within the columns in the denominator. That's why you will often see this as an F ratio that is between divided by within. Between the columns divided by the variance of the data within the columns. So let's go ahead and actually put some numbers in here. Let's find our degrees of freedom first. So remember, the degrees of freedom for SSC was C, the number of columns, minus 1. So in this case, it's 3, because we have 3 columns, minus 1, which equals 2. So the MSC equals the SSC divided by that degrees of freedom, which is, of course, 2. Now for the SSE, so the degrees of freedom for the SSE was n minus c. So n is 21, that's the number of overall observations, minus 3, which is the number of columns, so that is 18. So our MSE equals the SSE divided by that degrees of freedom, which is 18. Now the degrees of freedom total, the SST, is n minus 1. So our overall number of observations minus 1, which of course is 21 minus 1 equals 20. Now our F ratio remains the same. It is still the MSC divided by the MSE. Now let's go ahead and go into Excel and figure out the SSC and the SSE, which will allow us to find the MSC and the MSE that we need to do this problem. So here we are in Excel where we're going to do our hand calculation of this ANOVA problem. But before I give you a tour of our spreadsheet here, I want to draw your attention to the yellow box up here at the top. Now remember, we're going to need the sum of squares. However, Excel does not have a sum of squares formula. So what we're going to do is we're going to use the variance formulas and then alter them a bit. So the Excel variance formulas, which is var.s and var.p, which is sample variance and population variance, do the averaging step we don't want. So the sample variance will divide by n minus 1, and the population variance will divide by n. Therefore, we will have to sort of, quote, undo that step and make a couple of other adjustments to get the sum of squares we want. So in the calculations we do, in the formulas we use, you will see multiplication added in. That is the undoing of the variance averaging, and other multiplication that's in the SST, the SSC, and the SSE. So what I'm saying here is that some of this you're just going to have to take on faith. and I hate saying something like that in a math video, but that's just the way it is. I did not go over the individual SST, SSC, and SSE formulas because I thought your face would glaze over any more than it already is, and you can find those in your books. However, I will try to point out what each component is when we put in the formulas. Okay, so that's sort of my little caveat here. Now in the top left, you will see our chart, our data, as we had it in the PowerPoint portion. So we have our year 1 scores, our year 2 scores, and our year 3 scores. Nothing much surprise there. And then we have a column summary, so the mean for year 1, year 2, and year 3. And then we have the overall mean there in the middle. Now over on the right-hand side, I just put the formulas for the sample variance and the sum of squares we're going to be doing. If you're really not interested in the formulas that much, just ignore those 2 blue boxes up there in the right-hand side. Now if you look below our data, you'll see N and C. Well, N, remember, is going to be the total number of observations we have, which in this problem, of course, will be 21. C is the number of groups or columns or treatments we have. So in this problem, it will be 3. Now, over on the right, you'll see the SPSS output for this problem. So what we're going to try to do is replicate that little chart over there on the left-hand side where we have the green header and then the SSC, SSE, SST there in that chart. So we're going to try to make that chart on the left look like the SPSS output over here on the right. And of course, we will actually do this problem in Excel using its ANOVA. So we're going to have 3 versions or 3 outputs of the exact same thing to make them all match. Now, everything else on here is pretty much a hint, so we don't have to go back to PowerPoint to find these formulas. So below there on the left-hand side, you will see the MSC, the MSE, and the F ratio. And again, those just come from our slides we already had. Now in the purple boxes in the lower right, those are the formulas we're going to use to actually find our sum of squares. So I will explain those further when we get to that step. But I just wanted to put them here sort of in a text format so you can copy and paste them into the proper cell. So let's go ahead and do some actual calculations and put in some data. So the first thing we're going to do is we're going to go over to the N and the C boxes over here on the left-hand side. So this is easy. So our N in this case is 21. So we're going to go ahead and put 21 there. That's the number of observations we have. And then C is the number of columns, which is 3. So we'll go ahead and do that. Now the next thing I want to do is find the column means. So we'll go up to the year 1 mean box, which is the bottom of the year 1 scores, and then we'll use the average formula. So we'll type equals average, and I'll actually go ahead and begin filling that out. Now we'll just select all 7 of those scores in the year 1 column, close parentheses, and there we go. So this is 71.71, which is what we had in the PowerPoint. Now we need the mean for all 3 columns, so we'll go ahead and do the same thing for year 2. And we'll go and do the same thing for year 3. In case you're wondering, I don't drag across because it takes the color with it. So they would all be blue if I dragged across. Okay, so we have the column mean for each of the student years. So 71.71 for year 1 students, 75.29 for year 2 students, and 76.57 for year 3 students. Now we want the overall mean, which is in this gray box here below the yellow box. So again, equals average. And then we'll select all 21 scores in our data and hit enter. So now we have our overall mean of 74.52. So again, using Excel, we did hand calculations of all 3 column means and the overall mean, which of course we know we need to do this type of problem. Now let's go ahead and go down to our chart over here on the lower left. Let's go ahead and find the degrees of freedom for each source of variance. So remember, we have column variance, sort of between the columns, we have within each column variance, and then we have the total sum of squares, the total variance. Okay, so remember that for the SSC, we can see this sort of over here on the right-hand side. So degrees of freedom between, which is the same thing as SSC, is C minus 1. So we could say equals C, which is this cell right here, minus 1. And of course, that is 2. Now we need degrees of freedom for within. So that is N minus C. And you can see that little box on the right to help you sort of cheat a little. So equals N, which is that cell, minus C, which is that cell. And that gives us 18 degrees of freedom. Now our total degrees of freedom is N minus 1. So this is going to be equals N, that cell, minus 1. And that is 20. So that's very, very easy. Now comes the hard part. Now we have to find the sum of squares. Now I went ahead and put placeholders in our chart over here on the left-hand side so we know where everything goes. So if you look in the SS column, we have SSC, SSE, and SST. Sum of squares column, sum of squares error, and sum of squares total. Now in the lower right, you will see boxes outlined in sort of a purple color. So those are the actual formulas we're going to put in each one of those cells. So let's take a look at each one very briefly. Now there might be some multiplication in here you don't fully understand because I did not go over the actual formulas for SSC, SSE, and SST because they are mind-numbing. You can find them in your book, and the way we're doing it, you really don't have to worry about it. And that just sort of brings up my overall point. The chances of you having to do an ANOVA by hand are basically 0. At least I hope not. You're going to be using Excel or SPSS or Minitab or whatever else it might be. So we're doing all this by hand just so you can see how everything relates, not because you'll have to do it that often and hopefully never. So let's look at the top one first, and that is SSC. So in this one, I'll go ahead and put my mouse in there. You can see that we have SSC equals var.s. That is the formula for sample variance. And it's going to be cells A10 to C10. Let's go up here. What is A10 and C10? Well, that is the column means. So it's going to look at the variance of those 3 column means. And then we multiply by 2. Well, where does the 2 come from? In this case, the 2 comes from the number of columns we have minus 1. So basically, that's the same way of saying it's degrees of freedom. So that's where that 2 comes from. Where does the 7 come from? Well, that's how many observations we have in each column. So var.s is the variance formula, the sample variance formula for those 3 column means, times 2, which is the number of columns minus 1, so that's 2, times 7, which is the number of observations in each column. So let's go ahead and go over here to our SSC box. I'm going to take out the text. Then I'm going to go over here and copy our text in our box. We'll go back over to the SS cell. We'll paste it. Now I'm just going to take out the SSC part. So delete, 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 hit enter, and there we go. So the sum of squares for the columns, or the between sum of squares, is 88.667, repeating. So let's go ahead and look at the SSE formula, and it is admittedly much more involved. But if we take it apart, we can see where everything comes from. So we're using the var.s formula again, so that is the sample variance. Now the first one asks for cells A2 through A8. Well, what are those? Well, A2 through A8 are the data points for column 1, or all the year 1 scores. So we're asking for the sample variance of those 7 scores. Now we're going to multiply by 6. Well, why are we multiplying by 6? Well, that goes up to the formulas up here at the top. The sample variance is n minus 1 in the denominator. Well, we do not want that. We want to undo that. So that's why we're multiplying by 7 minus 1, which of course is 6. Then we're going to add to that the variance of the next column. So B2 through B8, same thing, times 6. And then we're going to add that to the variance for 3. So C2 through C8. So that is all that is. It's just the variance of each column added together. So we'll go ahead and copy all that. Well, first we'll go over to SSC and delete it, make room. Now we'll go over, copy all that, Control C on my PC, Control V to paste it. Now I'm going to go up and modify it by taking out the SSC at the beginning, delete. Then we'll hit enter. And there we have a sum of squares within, or an SSE, of 2812.57. So that is our sum of squares of the within. And again, that's within the columns. We just add them all together. Now we'll go to SST, sum of squares total. So we'll delete that. Now if you look down here in our formula, we have SST equals 20 times var_s of A2 through C8. Well, what is A2 through C8? That's everything. So A2 through C8 is our entire data set. Now, we take the variance of that and we multiply it by 20. Why? Well, remember our variance is n minus 1. So we have 21 scores minus 1. We're going to need to undo that, put it in the top. So that's why we multiply by 20. So we'll go ahead and select all that. Control C to copy. We'll go over to our SS column here, the SST. Control V to paste. We'll take out the SST at the beginning. Hit enter, and there we go. Now, if you look close enough, you will see that the SST is the sum of the SSE and the SSC. So 88.6667 plus 2812.57-ish. When you add those together, you will get 2901.23. So that goes back to the idea of partitioning the total variance. So our total variance of SST is made up of two components, the SSE and the SSC. When you add those together, you get the SST in return. Okay, so a few more things to do. Now we need to find the MSC. So that's up here under the MS column. Now if you look down here, well, I have the little formula for the MSC, or the mean square of the columns. So we're going to delete the text, and this is just the SSC divided by the degrees of freedom for columns, and we have both of those. So this is equal the SSC, which we just found, which is over here, divided by the degrees of freedom for the SSC, which is to the left of that. So we go ahead and click that cell and hit enter. Now we have a mean square for the columns of 44.3333 repeating. Now let's go ahead and do the MSE. So we'll delete the text in that cell. So this is the SSE divided by its degrees of freedom. So we'll go to that cell that we already have selected. This is equal the SSE, the 2812.57-ish, or whatever it was, divided by its degrees of freedom, which is to the left of it, that's 18, and we'll go ahead and hit enter. And that is 156.257. So now we have our MSC and our MSE. Now what is F? Well, F is merely division. The MSC divided by the MSC. Of course, we have both of those. We just did them. So the F here equals the MSC, which is there to the left, divided by the MSE we found, which is there. Hit enter, and you'll notice we have 0.283726, etc. What was it in our SPS output? Look over here on the right. Our F is 0.284. Same thing. So look at the SPSS output over here on the right and our chart we just did over here on the left. What do you notice? Degrees of freedom for the between groups is 2. Degrees of freedom for the within is 18. Degrees of freedom total is 20. The sum of squares for the between is 88.667. It's in both. The within sum of squares was 2812.57. Same in both. Sum of squares total, 2901.238. Same in both. So in Excel, by hand, we just replicated the output SPSS gave us. So now you can see how everything works together. Now, of course, I do admit the only odd part of this are these formulas down here. And again, you're just going to have to look at them and figure out where everything is being pulled from. But you're very smart, and I know you can do that. So let's do one more thing, and that's actually use Excel's built-in ANOVA to see if we get the same thing. So we're going to go ahead and go up to Data here at the top of the ribbon. Go all the way over to the right, and you'll see Data Analysis. So we'll click on that. Now remember, we are doing the ANOVA single factor. So go ahead and click OK. Now this wants the input range. So we'll select the little icon on the right, and then we'll select all of our data. Actually, I'm going to select the column headings too. All right, we'll go back. It's grouped by columns. We have labels in the first row. Our alpha is 0.05. We're going to stick with that. And we'll leave it to new worksheet apply. Those will give us all of our results on a new worksheet. We'll go ahead and click OK. And here we go. So I'm going to go ahead and spread some of these columns out. Okay, now a few things to look at. Well, actually, a lot to look at. So you can see that we have a summary of each score group. So year 1 students, year 2 students, and year 3 students. So it gives us our count, the sum of all those, the average, and the variance in each column. So we'll go down to the bottom. That's our actual ANOVA table. So you can see our between group sum of squares, 88.66667. Same thing. Within groups, sum of squares, 2812.57. Same thing. Total sum of squares, 29.24. Same thing. Degrees of freedom, 2, 18, and 20. Good. Our mean squares for the between or the columns, 44.33. Good. Our within mean square, 156.25. Very good. Divide those. We have an F of 0.2837, etc. Same thing we had before. Now this gives us a few more bits of information which are helpful. Now remember that when we're doing this sort of problem, we're going to test our F value of 0.2837 against an F critical value in the F distribution based on our degrees of freedom in the numerator of 2 and our degrees of freedom of 18 in the denominator with an alpha of 0.05. We learned how to do that a long time ago. So our F critical is 3.5545. So is our F statistic of 0.2837 larger or beyond 3.554? Well, no. So we would fail to reject our null hypothesis that these three means are different. So let's go back to our original. And you can see that all of this is the same now. So our SPSS output we set out to replicate, we did by hand over here on the left, and we did it in Excel using its built-in formula. Now, of course, that's the whole point. We will not do this by hand. We will either use Excel or we'll use some other statistical package. But I wanted to show you where all this information comes from so you can understand the foundation, sort of the guts, the workings, the gears of the ANOVA process. So let's go ahead and go back into PowerPoint and finish everything up. Let's go ahead and put in our numbers from Excel. So remember, in Excel, we found that the SSC, or the sum of squares in the columns, was 88.67. Then we divide that by our degrees of freedom, which is 2, and we end up with an MSC of 44.33. Now the MSE is the SSE divided by 18. So that was 2812.57 divided by 18. And that comes out to an MSE of 156.25. So remember, our F ratio here is the MSC divided by the MSE. So the mean squared of the columns divided by the mean squared of the error. Or you can think of it as the mean square between divided by the mean square within. So that is 44.33 divided by 156.25, and we end up with an F statistic of 0.28. And that is exactly what SPSS gave us and what Excel's own built-in ANOVA calculator gave us as well. So we know we did it correctly. Now, how do we ultimately interpret this? So our F ratio is the MSC divided by the MSC. That's what we just did. Now in the numerator, we have a degrees of freedom of 2, and in the denominator, we have a degrees of freedom of 18. So remember, when we look up a critical value in the F distribution, we have a numerator degrees of freedom and a denominator degrees of freedom. And in this case, those two degrees of freedoms come from our formulas for the MSC and the MSE. So we can write this F statistic we got to find like this. So we have an alpha level, say 0.05. Then we have degrees of freedom of C, of the columns, and degrees of freedom for the error, E. So that is the degrees of freedom in the numerator and the degrees of freedom in the denominator. So we could write it like this. So we need to find the critical value of F with an alpha of 0.05, a numerator degrees of freedom of 2, and a denominator degrees of freedom of 18. And we already learned how to do that in a previous video. Now the easiest way is to go into Excel and use the f.inv.rt function. That's the F distribution, the inverse, right-tailed, that's what all that stands for. And then we put in those three parameters. So an alpha of 0.05, a numerator degrees of freedom of 2, and a denominator degrees of freedom of 18. So when we put that into an Excel cell, we will get an F critical value of 3.55. So we have to ask ourselves, is the F statistic in our ANOVA table larger than our F critical value? Well, no. So remember what our null hypothesis said. We talked about this in the first ANOVA video. And these type of problems, our null hypothesis is that the means are equal to each other. Or it's another way of saying that the means, the three means, come from a common population. So since our F statistic is so low and does not exceed the F critical value, we fail to reject our null hypothesis. So we found no significant difference in mean test score by year of student. So the means of the first year students, the second year students, and the third year students on their study skills exam did not differ significantly. And that's it. So remember, up to this point, we could only do comparisons involving two populations, independent samples t-test and matched sample t-test. Limiting ourselves to those two comparisons is, of course, limiting. What if we wanted to compare the means of more than two populations, like we did in this problem? What if we wanted to compare the populations each containing several levels or subgroups? So this hints at the two-way ANOVA. So imagine a scenario where we have year 1 students, year 2 students, and year 3 students. But on the other axis, we divide them into male and female. Now we have two factors. So our first factor is the year of the student, and our second factor is their biological sex. That would be a two-way ANOVA. And we can do that, of course, using this technique. So the analysis of variance is the tool we use to do those more complex analyses. Okay, so that wraps up part 2 of our video on the one-way ANOVA, or the one-way analysis of variance. Now I know it was a lot to digest, but I really wanted to take you from the very basic conceptual foundations up through an example problem so you can see how all the data is related to each other, learn how to do the sum of squares, and then eventually find the relationship between those sum of squares, because that is the foundation of how we conduct the ANOVA. So I have no doubt that you may need to go back and watch parts of the video to really grasp it. But hopefully after watching it, you have a really good, solid understanding of what ANOVA is. So a few reminders and then we're done. If you're watching the video because you're struggling in a class, stay positive and keep your head up. You're an amazing, smart, talented person. Never let anyone tell you any differently, including yourself. If you like the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. Feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. It's always nice hearing from you. And finally, just keep in mind that the fact that you're on here trying to learn, committing yourself to improving as a student or as a business person, that is what really matters. I firmly believe if you have the right learning process in place, the results will take care of themselves. So, thank you very much for watching. I wish you the best of luck in your studies and in your work, and I look forward to seeing you again next time.